So I tried to do a little searching to see, what sort of things were there, about it. Because, what they're hinting at is you can buy a big software package to do it for you. And you might say, well, why would I do that? I just saw how easy it is to make these calculations. Well, yeah, that's because, I've got 10 lines of data, one product. And so I looked and found this example. In fact, I think I put the reference up there. Yeah. It's a company that worked with several big companies, and Honeywell was one of them. They sell their software for forecasting. And so you say, well, why would you do that? And you look down, scroll down a little bit. Honeywell had 32,000 pieces of data that changed per week. So they had, hundreds of products, if you will. It's their safety group that sells, safety glasses and hats and stuff like that. And you can see how, $800 million in sales. You're probably exceeding the number of rows and columns of things in Excel. You don't want to do that. They had somewhere in here they said they had 5 different pieces of software. So you can see why you might go to a company that makes this forecasting software, and they're going to give you some value for your dollar. They're going to interact with your SAP system or your enterprise resource planning system. They're going to suck your data in. They're going to do more than just write a little naive forecaster and give it to you. And so you can see why a large company would have an incentive to go with a third-party provider. And they were saying, what was their problem? They had 3 different systems for creating forecasts. There it was. They had a lot of different products. They had lumpy. I like that. That's a firm term. Lumpy, inconsistent demand. That sums it up right there. But anyway, they went with this company. And of course, this little thing's going to sound real good because it's a sales. It's a success story. But it was when you scroll down and read, it's only one page. Yeah. Here they looked at the first 3 quarters and their forecast. They're using. I thought it was good because they're using that measure, right? That mean, average, percent error. The MAPE that we just saw in our equations, and you can see it's getting better on their predictions. So of course, the software is great and everything. But anyway, the point is they talk about companies that will provide you with third-party forecasting tools. And again, I want you to think that they're just some little Excel thing that does a naive thing. They're far more sophisticated for a far more sophisticated problem. Not probably what you're going to have on a capstone, but you can see how the whole Y12 could need something like that. Anyway, so I just wanted to expound a little bit on that because I don't feel like they really talked much about it in the chapter. There's one last view graph here at the end. In fact, we're almost done with them, and I think we'll be done for the day. But let's see. Yeah, because I've only got a few more. So let's see. We talked about, there's the MAPE that they used, the mean absolute percent error. So they were using that one. So they were going to kind of end with an example, and then the last view graph that I promised. They're going to talk about Will State University, and you don't really have to take any notes on this because I don't think they have any particular formulas. I can't remember, but I don't think it was that sophisticated. But she's Irby's making got 2 different forecasting models, and she's trying to figure out which one does better at predicting, the number of walk-in students she's going to have in the advising center. All right, so here's her 2 models. This is actually what happened each week in the advising center. And here's model 1, and here's model 2. So one way to look at them is just plot them, right? See which one looks better. All right, or calculate some of these errors we've got. So let's see. So here was your actual demand. Here's model 1. Here's the error. It was 2 too high, 4 too high. Here's the absolute value of the error. And here's the absolute percent error. So down here, there's the mean absolute percent error, the MAPE. Right? Here's forecast model 2. Here's the error. Here's the absolute error. Percent error. All right, so right off the bat, you could say, from any metric you're going to use, whether you're looking at the mean forecast error or the mean absolute error or just the absolute deviation, all 3 metrics tell you to use forecast model 2. You know, you could have just plotted them too and looked at it and said, well, you know, it's like 2 is doing better than 1. And, you know, this type of simple model, I think, you know, this type of level of stuff would be fine on a capstone project if you're trying to predict something or use, you know, you get some data where you don't have any. So yeah, the conclusion is what we just said. Oh yeah, she also made a tracking signal, the last thing, which was that one that looked like an odd measure, you know, the one that had the summation of the errors divided by the mean. So there's that. And you say, well, what were you saying about it? Well, it is, in a sense, gives you a feel for your running error. So look, she's doing the tracking error just for model 2. So here's your demand, here was your forecast, and here's each of the errors, and then here's a running sum of the errors. So you can look as a running sum. Initially, you're kind of doing bad. You got a period of time in here where you've got a pretty big deviation. Your running sum is not getting any better. Your model is not tracking. It's gotten off track. Oh yeah, those words make sense to us. But as time goes on, it's gotten back on track. Your running sum of the errors is almost 0, which that'd be nice. That's right on track. And that's what this tracking signal is showing. Look, in this period where you were off track, this tracking signal, that little calculation of the sum of the errors divided by the mean, is big. And as you start getting on track, it gets small. So it gives you a feel for what that tracking calculation was. It's a measure of how on track you are as performance over the whole time period, since it's got all the sum of all of them. All right, so here, this is what we just talked about at lunch. If you've got a big enough history and enough data, you may want to go to some third-party provider. All right. And then here is the collaborative planning, forecasting, and replenishment. This is just a definition. And all they're saying is, hey, if you're going to do forecasting and you're in a piece of a bigger supply chain, hey, why don't you involve everybody, right? Yeah, why don't you get all the people in your supply chain, everybody exchange data. Let's all forecast together, the suppliers and the consumers and, you know, everybody along the supply chain. Wouldn't that make sense and make things better? Yeah, and then you would probably need one of these third-party companies to come in and do all that for you. So, there. Case study. Yeah, good time, because it's almost time for Dr. Garcia again. So the book has this case study. It's a company that makes golf balls and golf clubs, and they got a few questions on it, so I'll do it for us while we're eating. So what I did this time, rather than have to read it to you, it's in the book, but I just got a screenshot of the data. So the bottom line of the golf club example is this company's making 3 different drivers, the Bomber, the Hook King, and the Sir Slice-A-Lot, and they've got their demand, if you will, for each of them monthly, and they've got a couple of years of demand. That's what I got on the slice here. That year, January 2015. In fact, they've got 3 more months in 2016, right? January, February, and March. Okay, and so they got a couple of questions they want to deal with. They want to develop a model of this demand, and they can develop it either way. They can do it per driver or an aggregate. And they're going to do an aggregate. And then they want to know, according to the model, when will they have to have this new work cell up and running? And what new work cell? Well, that's the part I didn't show and what I cut. They say they can only make 2,700 drivers with their current work set up. They need to make a new work cell if their demand exceeds 2,700. And you can see from the graphs here, let's see. Well, we're not there yet, right? We're at 1,700, 500, 400. So we're at 2,600. So we're close, right? So we're almost there, and they want to know when in 2016 they're going to reach that, so they can, meet their demand. And then the last little question is, the vice president just went to China. He's worried that they ripped off their new club technology, and they're going to start making cheaper versions. What's this got to do? What do I need to know relative to that? So it's a little discussion question. All right, so what do they offer as a solution for this? I've already got it pulled up, I believe. Yeah, here. Yeah, I had it up. So what they did, just to give you an idea, they took, these are the months, and these are the 3 different clubs. And rather than do a model for each one, which you could have done, there's no problem, they just looked at the aggregate, because they're using the same factory to make them all, they can make one or the other, that's the assumption, that the work cell is going to be making any of the 3. And so they just summed up the demand. Okay, so they got the total demand over here by month, that's the red column. Scroll on down. And then the little one in the box is their prediction. What kind of model did they make? Oh, they just did a linear regression. All right? So they just selected the demand was their data, right? The sum aggregate demand, the red column, and their X values was the month. Okay? And so they did this linear regression. They've got an intercept and a slope. So the period, that's the counter, the month counter. So now they got a model. All right? So the linear regression model fits well. Why do they make that conclusion? Because R squared is almost 1. And again, we'll learn that statistic. We'll learn exactly what that means. And we'll look at several different sets of data and look at cruddy R's and good R's squared. And we'll know, and we'll look at exactly how you calculate it, so you won't just be able, you won't have to wave your hands when people say, what's that R squared really? Which is good. So the model does well. They've forecasted demand starting after March, April, May, June. Look at here, in August, they reached the 2,700 mark. So there's their answer to the other question. When do we have to have our work cell up and running? August. So given some lead time, 3 months or whatever, you might want to start in May. So you can see the utility of this. You can communicate to the vice president, hey, let's get things rolling in May so we can gear up in August. And then finally, what do you do about the Chinese thing? Yeah. Well, you know, how certain are you about your data, your information? Are you going to get your legal department to fight the patent infringement? Good luck. You know, my approach would be not to patent anything, just hide it. You know, trade secrets, which is, I've talked to several companies, that's what they do. A lot of, yeah, patents a good way to, in fact, we use patents all the time as ways to find out what technologies are out there, which is, so anyway, interesting. So that's the case study. And like I said, well, you saw actually what that was. That's posted. So those are all the homework problems except for this chapter. So if you've got any of these techniques you want to look at, just look at one of the problems that are on here. So you can go and look at any of the techniques that I didn't cover in detail. Actually quite a good set of homework problems in this chapter. And then the last thing I want to remind you of, if you're making these models, you know, everybody always gets annoyed. How do you show me your technique is working? You know, and I showed you that little tool where you can make up data, but they're still going to say, well, that's made up data. That's not real data. That's not my data. Yeah, great. You've got the ability to take data and predict right in your own hand, right? Think about it. If just like the golf clubs, if I've got, you know, time and some data, I've got, you know, 1, 2, 3, 4, 5, et cetera, et cetera, et cetera, and I've got a bunch of data over here. Well, look, why don't I just use this set as my data, and why don't I predict this set down here? This is my unknown, even though we know it's not unknown, right? It's, you know, we know it, we got it over here, but, you know, this will be my data, and this will be my predict, and then I can check my prediction with the actual values, and I can do that for this window and that window and this window and that window. I can do it for a bunch of different windows. I can really understand what's going on with my system, not the made up trend and the sine wave and the random thing idea. No, this is a real data coming out of your real thing, and it's a way to calibrate it and show to people, yeah, okay, I've got a model. Now again, you know, there's always caveats. The first law we said that it's always wrong. There's always some wrongness in there, but boy, isn't this a nice way to calibrate? And so do that, right? Do it. Got some data, predict, and play with the windows, play with the size, see how it does. Then you can really, I think, be fairly sure that you've got a decent model, at least like we said in law number 2 or 3, I forget, at least for the short term. Again, you know, start pushing it out 5 years from now. No, forget it. Too many things change. But if you're doing like the golf club guys and trying to determine over the next 6 or 7 months, you know, when we should get this work cell up and going, that has nothing to do with the Chinese. They're not going to sell golf clubs yet, I don't think. And so this is the, to me, the best technique for showing that your systems work, that your model's good, and also, magically, getting a quantification on the error, which is always what you want to do, because that's the first thing people are going to ask. Okay, you got your model. How certain are you? Can you put some error bounds on there? And again, I'm always pushing that. You know, come up with some error bounds on everything you do, even if it's just simple sensitivity type created error bounds, because at least your communication is more intelligent. You know, it's not saying the demand is 67. No, it's between 63 and 70. Yeah, that's okay. You know, if you want me to give you the most likely, I could say 67, but at least I'm giving you a bound or some, you know, some idea of some uncertainty. It's so important. And so you know, you've got that in your hand. It's there. It's there for you to verify your model with. So that's that for this chapter. I think I hope you think it was fun. And now it looked hard, but I don't think it was. I don't think any of these equations are hard. I don't think the linear regression is hard. Again, you want to play with it before you deal with it and make sure you understand what it's producing. And we'll know more from the statistics viewpoint later on. But it's good technique. It's something you can use, I think, to predict anything. No, core all season if you want. So now I guess it's 12:30. It's time for Garcia. He should come right on in, right? On cue. That's it. Yeah, it's like a play, isn't it? Yeah. And see, it was Cowboy Day. He should like that.
Yeah.